Okay, Newton's third law, here we go. For every action, there's an equal and opposite reaction. And forces come in pairs. And they always come in pairs. So you need to put that here. Forces always act on pairs. Now each force of the pair acts on a different object. So that means, you got your notes out, James? So each force of the pair acts on a different object. So that means for the free body diagram, you only put one of them. That's key. Okay, for a free body diagram, you only put one of the forces from the pair. Oh, it's the last bullet. But yeah, it's so important I mentioned it twice. So I was going to show you a video here, but I thought it would be awesome, but it's actually not. So we're moving on.
Why is it not awesome?
Because I thought it was The Matrix, but it was just Bill Nye from like the 80s. Okay, so in space, like, you don't really have anything to push off of in a sense. You're just in the vacuum of space. So how do these guys get around? These, yeah, these little thruster packs. So how does he go forward? He's got to thrust. If he wants to move forward, he would have to thrust backwards. Yeah, so you have to push the opposite way so that you get moving in the direction you want. It's exactly like that. So for a fish, the fin pushes on the water, but then the water pushes back on the fish. And that's how you move. Have you ever swimming with flippers? You guys ever done this? Swimming with flippers? You can get going pretty good. You guys have seen the movie Gravity? Have you guys seen this? Yeah. So it's pretty wild. Yeah, we should at the end maybe. Yeah, Interstellar, that's an amazing movie. Fifth Dimension, yeah. Okay, how about the next one? The baseball pushes the glove left. The baseball pushes the glove left. So what's the other force pair that goes with that? The baseball pushes the glove left, so then the glove pushes the baseball right. It's like the opposite. The bowling ball pushes the pin left. The pin pushes the ball right. Right, but they always make a contact force, and they always have these equal and opposite forces. Always. So the fish swimming, the bird flying, and sitting on a chair, they're all examples that are easy to visualize. How does a fish move? How does a bird fly? And how do you sit on a chair? Like, why don't you just fall through the chair?
Because chairs are solid.
Your body, namely your butt, pushes down on the chair. The chair pushes up on your butt. And those two forces are equal and opposite. Always. While driving down the road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus and the bus hit the firefly. Which of the two forces is greater, the force on the firefly or the force on the bus? They're equal. Good. They're equal, but the masses are different. So that force obliterates the fly. And the bus moves on like nothing even happened. It's the same with the bowling ball and the bowling pin. It's the same force applied, but because the bowling ball weighs, or not, yeah, has more mass, the pin goes flying, but the bowling ball pretty much goes the same direction. Okay? So that's a common misconception, number one there. So you need to put that the forces are the same.
Forces are the same no matter what the mass is.
The forces are the same no matter, like, for any situation, the action-reaction pair. So that's what you're looking for. Action-reaction pair. Action-reaction pair. Yeah, action-reaction pair. No, mass does dictate force. The more mass you have, the more force you'll have. No, the force is the same. It's a different acceleration.
Wait, so if the more mass you have, the more force you have, then the bus has more force, right?
No, 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 no. The forces are equal. The masses are different, and therefore the accelerations they experience are much different. Force is equal. Mass is different. Therefore, acceleration different. The firefly basically has all his particles become a goopy mess, whereas the bus is like unaffected completely. Same with the bowling ball. Bowling ball, bowling pin. When they strike each other, make contact, they push on each other. One pushes on the pin pushes on the other. And the forces are equal in magnitude, opposite in direction, but their masses are different, so then therefore the accelerations are different. That's according to Newton's second law. Force is directly proportional to... go the other way, my bad. The other way, my bad. The acceleration is directly proportional to the force. But more importantly, the force, my bad, the acceleration is indirectly proportional to the mass. So if the mass is very large, the acceleration is very low. It's indirectly proportional. So for the firefly has a very small mass, so the acceleration is quite large. And it's so large that his particles poof and become a goopy mess on your windshield.
Because it's so light, and so it goes in the air, and the air becomes
Yeah. We just
light on it, so it goes really fast.
So we have to use the proper wording. Like, there's a difference between weight and mass, so like you have to talk about its mass. It has a small mass. Yeah. The bus has a large mass, and therefore a low acceleration. Good. So many people are familiar with the fact that a rifle recoils when fired. You guys ever seen that? Shoot the gun, and then it like goes into your body. Yeah. There's lots of really funny fail videos on that. Yeah. Now, no. Now, this recoil is the result of action-reaction force pairs. The gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward on the bullet. So the rifle pushes the bullet forward, Yeah, the rifle pushes the bullet forward, so the bullet pushes the rifle backwards. The acceleration of the recoiling rifle is greater or smaller than the same size as the bullet. The acceleration of the rifle. Smaller because it has more mass. That bullet goes, if you shot that bullet straight and there was no ground to stop it, that thing would go for a long while, right? Because it's so small, or so much, has such small mass, right? But the rifle's much heavier. So that same force doesn't affect the rifle as much, but it affects the bullet a lot more. Okay, so that would be for C. Oops, my bad. Smaller. Okay, let's move on. Identify at least 6 pairs of action-reaction forces. Don't look at the answers. Let's look at the guy. What's happening right here? He pulls on the rope to the right. So maybe it's like, what is that, a tractor? So I'll put MT, force MT. The force of the man on the tractor, and then this direction is the force of the tractor on the man. What about on this side? Yeah, force of the elephant. Oh my gosh. Force of the elephant on the man, and this force would be the force of the man on the elephant. You guys feel okay about that? There's lots more, like the elephant pushes down on the ground, and then the ground pushes up on the elephant. Okay? Okay, and you can read more of those if you like, but we just did a couple. While at rest, do you think that's important? A 75-kilogram astronaut throws a 4.5-kilogram wrench. The wrench is accelerated over a distance of 1 meter, reaches a final velocity of 20 meters per second. Determine the magnitude of the force applied to that wrench. What is applying this force? What is the magnitude of the force acting on the astronaut? What is the acceleration of the astronaut, and what will the astronaut's final velocity be? So, you have this astronaut. He's at rest, apparently, in space. Okay? He has this wrench. And then he throws it. So you have this force from the man on the wrench. Forces come in pairs. Now I want you to imagine standing on that skateboard with a ball in your hand, a basketball, and then you throw the basketball. Do you stay motionless? Or does the skateboard roll backwards? So I wish I had a skateboard, but standing on it, if I put a force that way, why do I roll this way? I think you guys have seen this in your real life probably. So there's an equal and opposite reaction force. I throw the ball that way, that must mean I must get pushed this way. And if there's not a lot of friction, I'll notice it. Like if I'm standing on the ground though, I don't notice it, right? Okay, so there's the force from the wrench on the man. Equal and opposite. So if the forces are equal and opposite, I just need to find one of the forces from the information, and that will help me equate that over to the other side. So we have to use the information given to us, and you notice that you're given some kinematic stuff. You're given kinematic stuff because what happens is every unit of physics, whether it's physics 20 or physics 30, they will always give you kinematic stuff that you have to work with. Okay? So you have a distance, you have a VF, and you knew that VI was 0, and you're looking for, probably, what do you think you're looking for? If it's forces, MA, you're looking for acceleration. So which formula do you think I should go after, considering I don't have any knowledge about the time? Well, like, Maria, if you don't have time, see if you can just try to use this one right away. VF squared, VI squared, and 280. Yeah, if you don't have time. Now it reaches a final velocity of 20. So we have 20 squared on that side. The 0 squared is so nice. Now it's just 2a and d. D is 1. So look how nice that simplifies to. You got 400 on the left, 20 squared. What do you got on the right? 2a. Did you guys all see that? 0 squared is 0 plus 2 times 1 times a. So what is a? It's pretty massive acceleration. To get going to 20 meters per second in 1 meter. I bet that should be like 10 meters. But whatever, we'll go with it. So determine the magnitude of the force applied to the wrench. Well, force applied to the wrench, that would be the man on the wrench. That's going to be MA. Which mass do I use? It's a force applied to the wrench. Force is directly proportional to mass and acceleration. So which mass do you use? The 4.5, right? Because that's the mass of the wrench. So we have 900 newtons. In my picture, it's to the right. So if it's 900 newtons being applied to the wrench, what's the force being applied to the astronaut? Good, 900 newtons left. Because it has to be equal and opposite. Now here's the key understanding. Will the acceleration of the astronaut be the same? Because he has a different mass. Good. So now you have 900 newtons negative equal to MA. M is 75. Divide out the 75 and you solve for A. You get negative 12 meters per second square. So he accelerates 12 meters per second square to the left. It's okay, it's just a graphic calculator, I don't even need it. So what will the astronaut's final velocity be? you want to just use the same formula? Yeah, jump into it. See if you can get it quickly. Leave that final bullet. We're going to leave that final bullet because we don't have the distance the astronaut covers. All right, let's move on. Okay, Mr. Lionberg does a push-up. He's so strong that he actually pushes the Earth down with a maximum force of 35 newtons. Now, when I do a push-up, I push down on the Earth pushes up on me. When I push down, what happens to my body? It accelerates up. Does the Earth accelerate down? It does, but it's so small you would never even notice. Yeah, like if everybody did a push-up all at once, every single person on, I think there's a Veritasium video on this. You guys know Veritasium? Right. If everyone jumps at the same time, would the Earth be knocked off its orbit or something like this? You gotta watch the video. But yeah, like the the Earth is so massive that you would never, and that's what this question's all about. Okay? So you have this person doing a push-up. I don't know what a push-up looks like. Looks like this. I don't know. You push down on the Earth pushes up on you. So I push down with 35 newtons. I push down with 35 newtons. So if I push down with 35 newtons, the Earth pushes up with 35 newtons. So you got 35 newtons up, 35 newtons down, equal and opposite. So that covers the first bullet, 35 newtons. So what is my maximum acceleration? Well, F equals, what does F equal? ma. The force is 35, the mass is 98, so divide out the mass, and you get the acceleration. So I'll accelerate at 0.36 meters per second square. Now what's the acceleration of the Earth? I'm like Chuck Norris. I'm so strong, I do a push-up, the Earth moves. Okay? By how much? By what acceleration? So the force of me on the Earth, so Lineweber on the Earth, equals ma. I know the force is 35 newtons down. What's the mass of the Earth? 5.98 times 10 to the 24. That number you could find on your data sheet. Okay? On the back of the data sheet there's a list of constants. So when you divide that out and you solve for A, (5.9) times 10 to the negative 24 meters per second squared down is basically 0. That number is essentially 0. It's so small it's not even a value. So page 74, there's only 3 questions. So let's see if you can get that done in 15 minutes. Page 74, 3 questions. I'll leave this slide up. Twelve to 14. Let's see if you can get that done in like less than 15 minutes. Then we can move on. Did you guys actually use your class time yesterday? To use that to like 5 to 15 or whatever I assigned? Getting better at those force equations like we did on the whiteboard today? Because we got to just go through a few things before we can jump into some more complex problems. Yeah, I'd like to get into the next section, so see if you can hammer out this 12 to 14. Okay, let's move on. Basic forces. Is it the next place in the notes? All right. Okay, weight is the gravitational force exerted on an object, and it's measured in newtons. Mass, from a Newtonian perspective, is the quantity of matter in an object. For the higher levels, they actually revisit this notion of mass and relate it to like speed of light and stuff like this. But for everyday, like just solving regular, everyday macro world problems, mass is easily defined as the quantity of matter in an object measured in kilograms. Now your weight, or the force of gravity, and we got to be careful when we're in here. We're in a physics class, we're not in everyday life. So when I hop on the scale and my girlfriend's like, how much do you weigh? And I'm like, oh, I lost 5 pounds. Like, that's different than like what we're talking about in here, okay? So if you want to say if you want to say kilos, like you got to call it the mass. But if you say weight, you have to be in newtons. Weight's a force, mass is not. Sorry, that? Pounds would be mass, yeah. Pounds is mass, yeah. Okay, and here's your force of gravity formula. It's just mg. Okay, and you're going to use that one a lot in this class. Okay, and I wouldn't even go with, like, cross this out actually. This right here. Cross out that w. Like weight is just fg. Cross out that w. And your weight will change on other planets. And that's why you watch those videos of those guys on the moon, and they're allowed to like jump and soar through the air because they have less weight. Weight, like all forces, is a vector, and it's always directed down. So it will have a negative sign. And your weight varies. You go to Jupiter or you go to just outside the Earth, wherever you are, your weight changes. But the mass remains the same. Your mass is your mass, but your weight can change because weight is a force. So calculate your weight on Earth. You probably don't know how much you guys weigh in kilograms. Like a friendly estimate for me, I'm 205 pounds. You can do your weight if you like. So you just use your pounds. Some of you probably could guess your weight in pounds. You probably know it. Just divide by 2.2 and you get your kilograms. So you guys can do yours. So I'm about 93 kilograms. So then my weight is mg, 93, 9.81. I'm about 900 newtons. Okay, so my weight is about 900 newtons. So, Josh, how much do you weigh? Amran, how much do you weigh? Did anyone do this? Or you just copy me? Shalay, how much do you weigh? No, how much do you weigh? Yeah, we don't want your mass. That's good, Jed. That's good. How much do you weigh, Shalaya? About 600 newtons? Good. How much do you weigh there, Morley? About 700 newtons? Okay, you guys clear on that? Weight is a force. Okay? So the acceleration due to gravity on the moon is about 1/6 what it is on Earth. Find the weight of a 350 kilogram piano on the moon. Well, the force of gravity on Earth, the force of gravity on Earth would be this. But the acceleration due to gravity on the moon is 1/6 of that on Earth. So I just have to take this value and multiply by 1/6. So it's just 350 times 9.81 divided by 6. So remember on the last slide, I weighed on Earth about 900 newtons? So this grand piano, 350 kilogram grand piano, it weighs less on the moon than I do on the Earth. So it would be a lot easier to move a piano around, apparently. Yeah, but its mass is still consistent, yeah. You guys ever take baths or hot tubbing or whatever? Swimming pool? What do you notice? What do you notice when you're in the water? Do you feel as heavy? You don't feel as heavy, right? Does your mass change while you're in the water? So what makes you feel less heavy? What's that force called? What's that vocabulary word? It starts with B. Yeah, that buoyant force, it pushes you up. So then the net force acting vertically, like your weight pushes you down, but the water pushes you up. Not enough so that you float 100% perfectly, but you do feel a little bit less heavy when you're in the water, right? You feel less heavy, but your mass stays the same. Okay, Mike, he's got a mass. Here's the weight on the sun. If you could apparently stand on the sun. The acceleration due to gravity on the sun. So this is just very basic stuff. Put the force where it needs to go. Put the mass where it needs to go, and then you can solve for g. So just so you guys are aware, like that lowercase g is just lowercase a. It's the same letter. If I use g, it's just gravitational acceleration. Okay, so divide out to 60, and you solve for it. So you get 266 repeating. The unit for acceleration is meters per second square. Wow. Compare that to Earth. Like Earth is 9.81. On the sun, it's 266.66. You wouldn't want to get too close to that. This is what happened. You just get slammed into it. It feels so heavy. Oh my gosh. Yeah, probably. It's safer. Okay, the normal force. Now, I think we're going to actually Okay, before I just give you the notes, we're going to talk about the questions first, and then we'll go back to the notes. Okay, so flip ahead to this one. Determine the normal force experienced by a 45 kilogram person standing on a horizontal surface. Okay, this one you've seen before. Person standing on the ground. If you drew a free body diagram for that, what force acts down? Force due to gravity. Now there has to be a force that allows this person to balance there on the ground without accelerating. Right? This is at rest. If you're at rest, the forces must be balanced. So which force is it? Force normal. Force normal is always perpendicular to the surface. Always. Force normal is always perpendicular to the surface. Where this gets nasty is if you're standing on a ramp. Because then you're not exactly like vertical. We'll see in the next question. So in this case, because the person's at rest, the normal force is equal to the gravitational force in terms of the magnitude. Right? In terms of the magnitude. Are they equal in terms of direction? No, the forces are equal and opposite. So Fn in this case is equal to mg, which is 45 times 9.81. But back up a sec. The person who controls all the rules of physics has told me that it's mg cos theta, where theta is the angle of the surface from the horizontal. Wait a sec, where's my cos theta? But what is theta in this case? Theta, not cos theta. What's theta? What angle does the normal force make with the surface? 90 degrees, right? So go ahead and type cos 90 just by itself, cos 90. Cos 90 is not 0. Cos 90 is 0. The heck? Can't even remember my basic facts from trig. Yeah, cos 90 is 0. So this is a problem. Give me 1 second to collect my thoughts. My bad. The angle is not 90. The angle is 0. The angle is 0. The theta is the angle of the surface. So in our case, the angle was flat. So that would be 0 degrees or 180 if you wanted. But it's just 0. So now type cos 0, my bad. Cos 0. Cos 0 by itself. 1. That's what we're looking for. So what happens is that you just get mg times 1. Anything times 1 is just itself. Anything times 1 is just itself. So you get that the force normal is just mg in this case. Now what happens is when we move to the ramp, this is not true. This is not true. But students will always think that Fn equals Fg, always. But it's only true for flat surfaces. And just use 0 degrees for this formula. In fact, when I see this, I don't even think of that cos theta. I just go Fn is equal to Fg. They're directly opposite of each other. Now when we do the ramps, and we'll do a whole section on the ramps, this next bit here is just a warm-up. You won't have any inclined plane questions until we talk about them like for a whole class, because we have to do quite a lot of work for them. But we're just going to introduce it. So draw a right angle triangle at 30 degrees. So now the surface is no longer flat. The last question, the surface was flat. That was 0 degrees. For some reason, I thought the surface was vertical. That was a blunder. The last question, surface was flat, 0 degrees. Now the surface has been just raised a little bit by 30 degrees. So now when you stand on this ramp, which way does that normal force point? Back to the definition. What's the normal force? Always what to the surface? Perpendicular. So here's the normal force. You see how it's tilted? So Fn does not equal Fg. Because which way does Fg point? See how that works? Now we're going to leave that because we're going to spend a whole lesson on these inclined planes. We'll leave it for now. You can easily calculate the normal force from the formula, Fg cos theta, if you want to do that. You can finish this question off if you like. But the takeaway from this slide is that the Fn doesn't always equal the Fg. The Fn only equals the Fg on flat surfaces. So if you guys could take a look at these two questions before you come in tomorrow, that would be lovely. Just 2 questions.